Please go ahead.
Okay, thanks. Yeah. The work I will be presenting is joint work with Ilya, Kalmaria, and Gillard. All of us are based in Calgary, in Canada. So by now, you've seen everything you need to know about the basic of the research here, quantum thermodynamics. So here in this work, I will only consider one fixed background temperature, beta, and then of course every system has exactly one free state, namely its Gibbs state with respect to that background temperature. And well, notation-wise, since every state is only a resource if we know what its free state is, or if we know what the Hamiltonian is, we will always write this tuple of states. And earlier today, you saw the Hamiltonian instead of the Gibbs state. Well, it doesn't matter, right? But I chose the Gibbs state because, well, many Hamiltonians correspond to one Gibbs state, right? And for this work, only the Gibbs state is important. So you've also seen the thermal operations, so I won't talk about them anymore. The only thing I will mention is that, well, we work with finite dimensional systems. So also the system that we attach in its free state is finite dimensional. So this means this set of operations is not closed, right? So it can happen that you can approximate a channel arbitrarily well with a sequence of channels where the dimension of B grows unboundedly. So technically, we have to take the closure of these operations. We want to have a closed set. And in fact, this is what all the works I know in quantum thermodynamics implicitly do, but it's not mentioned very often. But mathematically, it makes a difference. Right? So another subtlety I want to mention is that, well, the system that we trace out is not necessarily the same as we attach. But what we demand is that our Gibbs state always factorizes in this, right? Because otherwise we cannot speak about equilibrium state of individual subsystems. And then it doesn't make sense to talk about, well, their equilibrium. So another piece of, and let me also mention, so I added the C to make clear that I'm talking about the closure of the thermal operation. So this is not the same as the C that was used for the catalytic earlier, right? So if we talk about cooling and heating, first we need to define what we mean if we cool and heat. And let me do this at the example of cooling, and then heating is exactly the same in the other direction. So I will always assume that the system A that I try to cool or heat is initially in its free Gibbs state. And then cooling can have at least two different meanings, and both are studied in the literature, and both have their relevance. So the first one that probably comes from a classical intuition is to bring the system to another Gibbs state that corresponds to a lower temperature. And the second interpretation would be to increase the overlap with A's ground state, which is probably what you want to do if you do, I don't know, Bose-Einstein condensation, or if you want to reset a bit in the quantum computation. Now, luckily for qubits, and if we restrict ourselves to thermal operations, the two interpretations coincide, right? Because we have only two levels. So if we increase the overlap of the ground state, well, this means we go into a lower temperature. Now, the task we are considering is what is depicted here. So we have one initial resource, the blue system, that is out of thermal equilibrium. We have our environment, or our thermal bath, at a fixed background temperature. We have the system we try to cool, which is initially in thermal equilibrium. And then we try to apply a thermal operation, right, which is done by applying this thermal unitary, which acts on the initial resource, the system we try to cool, and potentially parts of the environment. And the goal is to cool this target system as much as possible. Now, if we write this task in formulas, we are essentially studying a state transformation, right? So we start with our system, which is the resource put system, labeled by R, the system that we try to cool, which is in its free state, and we try to convert it with the closure to thermal operations to, well, a Gibbs state that corresponds to a different temperature, which is represented by the tilde. Now, of course, in this research theory, we can always remove and attach systems in the Gibbs state, so we can simplify the expression. Then it turns out for cooling and heating, coherences between different energy eigenstates, they are not useful. So without loss of generality, we can either assume that they are not there, or we can simply delete them, which is something we can do with thermal operations. So the P is a pinching channel, so this just deletes these coherences between different energy eigenstates. Now, both the initial and the target state, they are quasi-classical, right, in the sense that we can simultaneously diagonalize them. And then it's a very well-known result that the conversion power of the closure of the thermal operations is the same as the conversion power of the Gibbs preserving operations. Another consequence of now dealing with quasi-classical states is that we can reduce everything to probability vectors, as you already heard this morning in the talk of Campbell. So we extract the probability vectors from the diagonals of our matrices, and well, then in this case, the Gibbs preserving operations, well, they act on probability vectors essentially, so we can represent them by stochastic matrices. And then we are back to relative naturalization, like a special case of exactly the matrix naturalization we had earlier on the talk before, right? Now for the special case that we have only two vectors in our matrix. So yeah, we want to simultaneously convert, well, a vector R to a vector G tilde, right, corresponding to the Gibbs state at a different temperature, and preserve the Gibbs state. And this is exactly the definition of relative naturalization. Now, I thought about shortening this part because Kevin talked about it this morning, but I need some notation and it's quicker to go through the construction and just to introduce notations, so I kept it. So assume we have this pair of probability vectors, and what we want to do is we want to construct one of the Lorentz curves because it will show up in the results. So first, we find a permutation pi that reorders the two probability vectors simultaneously, such that R of Pj divided by G of Pj is non-directly similar. And then we sum up the first k coefficients of the reordered vectors in order to get points, right, in a two-dimensional plane. So let me give an example. If we have the vectors R and G, so four-dimensional vectors, well, those are already ordered in the way we want them to be ordered, then we can plot the lower Lorentz curve. So the lower Lorentz curve is like the x-coordinates are, well, the first x-coordinate is the third, right? The first y-coordinate is the 12th. Then we add the first two x-coordinate, well, the first two endpoints of R to get a second x-coordinate and so on. You add a point at 0, 0, and you connect. And this is the lower Lorentz curve. So I'm working with the lower Lorentz curve. This morning we saw the upper Lorentz curve, but I mean, one follows from the other just by a symmetry transformation. So now this lower Lorentz curve, I will introduce a function alpha y that maps the y values here to the corresponding x values in the lower Lorentz curve. This is just because it's easier to write down the results in this way, but of course you could also do it the other way around. So now why all of this? Because we have relative naturalization if and only if the lower Lorentz curve corresponding to the initial resource is always further to the right for every y value than for the target resource. And with the previous slide, right, where we reduced this cooling problem to relative naturalization, this essentially means in order to figure out how much we can cool or heat a qubit, or in general any system, comes to figuring out what happens with those curves. Well, you can do this, and then it's not very hard to find out, well, the maximum and the minimum temperatures to which we can cool and heat are given by those expressions. So, and of course, betas are the inverse temperatures. So they depend on a few things. Well, they depend on the background temperature, beta, right? If you already start at a higher temperature, well, we can probably not cool as much as we would start at a lower temperature. They depend on the qubit that we are trying to cool, namely its energy gap E. And of course, they depend on the initial resource that we have. Now, this is a closed form expression, right? And it depends on this function that describes the lower Lorentz curve. Importantly, well, the minimal so in a heated case, right, the maximum temperature to which we can go, or the minimum inverse temperature to which we can go, this can be negative. So this can have a population inversion if we have enough resources to begin with. Now, if you try to cool arbitrary systems and not qubits, then the solution looks a bit more technical. But, well, you can still write down expressions that now depend on an optimization over a finite set. Also, just as a quick remark, if you think about the second interpretation of cooling, right, trying to increase the overlap of the ground state, also this is exactly the maximum overlap that you can achieve is exactly given in terms of, well, this lower Lorentz curve, where the pi here is a projector onto the possibly degenerate ground state of the system we are trying to cool. Now, we know those minimal maximum temperatures to which we can cool and heat, and we can use them to define monotones, right? So we can define cooling and heating monotones, C and H. Again, for the fixed background temperature, for the qubit that we are trying to cool, and they essentially just tell us, well, how far away do we get from the equilibrium temperature where we are stuck. Right, so we have the different signs because, like, well, for cooling, we decrease the temperature, for heating, we increase it, right? So we want our monotones to have non-negative output, so we just take the different signs. So those are monotones, but obviously they have an operational implication, right? Maybe exactly this one, how much can we cool and heat? And they have a closed form expression because on the previous slide we saw the beta min and the beta maxes. Now, more importantly, and this is the main result, they completely characterize state conversions between quasi-classical states. So assume we have an initial resource, we have a target resource, and we assume that the target resource is quasi-classical. Then we can convert the initial resource to target resource or to go to some operations, if and only if for any fixed background temperature and all energy gaps or all qubits, the qubit heat, the cooling and the heating monotones are non-increased. So what does this mean operationally? Well, if the initial resource is at least as good at cooling and heating any qubit as the target resource, then we can convert the initial resource to the target resource. And to be very clear here, like the conditions for the conversion of quasi-classical states, they were well known, right? So this is not a new result. The new result is essentially giving the relative majorization or thermomajorization and interpretation in terms of cooling and heating of qubits. So, well, what does this result tell us? Well, it tells us the performance in two of the most elemental thermodynamic tasks, like cooling and heating. That's, well, besides work extraction, probably the most important operational thing we can do. And we do it on the simple systems, right, on qubits. It doesn't get simpler than that. And this is already enough to completely determine the convertibility within quasi-classical states. And in technical terms, well, the cooling and heating monotones together, they form a complete set of monotones. Now, a quick remark. Maybe those of you familiar with thermomajorization, they know, well, you don't need to, well, essentially it's enough to check k-1 conditions, where k is the dimension of the output system. So here we have the same. If you just want to check convertibility to one fixed target state, it's enough to check essentially the ability to cool and heat a total of, well, the dimension of S minus 1 qubits. But if you want to do it for arbitrary target systems, then you need all monotones back. Okay, well, so far we looked at how well can you cool and heat a specific qubit, right? A very related question is, which qubits can you cool or heat to a desired target temperature? And interestingly enough, this also completely characterizes the state conversion problem. So a bit technical at first glance, but let's say we define the set of energy gaps, or in other words, qubits, for which we can cool or heat them to the specific target temperature. Right? And then we essentially get exactly the same as the previous result. So again, we can convert the initial resource to a target resource. Now, if and only if we have this inclusion relation on the set of qubits. So in words, well, we can convert the initial resource to target resource if and only if the initial resource can cool or heat any qubit to any target temperature if the final resource can use. Okay, with that, let me come to the conclusions. So essentially, we solved the problem of cooling and heating with the problem of thermal operations, which is an application of thermal miniaturization. And as the main result, we saw that the ability to cool and heat fully characterizes the state conversion problem. And in some sense, I don't know, intuitively to me, this sounds like, okay, we have quasi-classical states, there's nothing quantum, right? So it's determined by some very classical tasks, such as cooling and heating. Now, technically, those are complete sets of monotons, and all the other operational interpretation flows from scratch. More interestingly, how can we generalize this, right? So, what happens if we want to talk about the convertibility between states that are not quasi-classical? Well, since our monotons are monotons, they are still necessary conditions, right? But it's also quite easy to see that they are no longer sufficient. For example, if you take a state, right, that the diagonal looks like a Gibbs state, then it's, well, for cooling and heating, it has exactly the same power as the Gibbs state. So in a sense, it's useless, right? But of course, you cannot convert a Gibbs state, well, to a state that on a diagonal looks like a Gibbs state, but has continuances, because the Gibbs state has to remain invariant. And in some sense, this cooling and heating problems, this is something that is also studied in other fields dealing with quantum thermodynamics, but not from a research theory perspective, right? Like all this autonomous cooling and heating engines and stuff like that. And so I think it might be interesting to compare the temperatures that we can reach to temperatures that those other models of quantum thermodynamics can reach, and then to figure out, okay, do we maybe reach the same temperatures? What's the difference? And this will tell us what is really the level of control that we need for different tasks, right? Because here we have as much control as you can have, right? We append an arbitrary large auxiliary system, and then we apply a unitary that acts collectively on this huge system. So that is as much control as you can get. And a lot of those like models of thermodynamics that come more from an applied direction, you have way less control, right? Maybe you have like one auxiliary qubit that you act on. And this, will tell us how much control is needed and how much power we lose if we restrict our control. With that, thanks, and I'm looking forward to your questions.
Now let's move to the discussion time. And do you have any questions or comments?
Thanks. So this has a very similar flavor to elementary thermal operations, right? Have you explored the connection, if any, like because of these two-level interactions?
Well, I'm cooling and heating qubits, right? But I don't think it's directly related to the elemental thermodynamic operations. But well, for sure, but you could say, right, those are a subset of the thermal operations. So with those, you can for sure reach, well, lower deviations from the initial temperature, right? But I'm not sure whether you can directly, like, just because we're cooling qubit doesn't mean we are restricting our operations to sequences of operations that only act on two-dimensional subspaces.
No, I'm not saying you're restricting to them, but I wonder if your results can lead to some kind of construction where we find a sequence of such exchanges or something.
Maybe yes, but it's not obvious to me how you do this.
Any other questions or comments? Then I have a question. You provide the character interpretation of the thermalization by heating and cooling, and then as it is well known that if we have a catalyst, then the characterization of thermalization completely becomes different, and then many infinite family of Rayleigh entropy characteristics. In your interpretation, what happens if the catalyst is introduced?
Yeah, very good question. The answer is I don't really know. So, well, again, of course, the results here give you bounds, right? But I have no idea like how much better you could cool or heat in some sense.
Okay, okay, thank you. Any other questions or comments?
Thanks for that. So, I'm just curious if you have any ideas how to address this first open question. Are there any natural heating, cooling, and task that takes care of coherence that can?
I mean, yeah, I guess it's very similar to what you said in your talk, right? Like essentially the cooling and heating monotons, they capture the non-uniformity aspect of thermodynamics. Right, so somehow you would need to add, like if you want a complete set of monotons for general state transformations, you would somehow need to add monotons that capture the coherence or superposition aspect.
Exactly. At least thought of like what kind of task might this be, or I mean.
Yeah, so okay, I was playing around a little bit with like essentially states, right? That if you decohere them completely in the energy eigenbasis, then they are the Gibbs state, right? Because they have no non-uniformity aspect, but they have potentially coherence. So essentially the pure state whose diagonal is the Gibbs state. And I guess this is also somewhat related to the talk of Jonathan, right? Because it's essentially then you have two sources of, well, resourcefulness here, the source of non-uniformity and the source of coherence. But really marrying them together, I don't know how to do that yet. Thanks. You're welcome.
Any other questions or comment? No, and then I will start the speaker again.